This is 1. And because this value divided by the red value here divided by the blue value here is almost 1. In the green case, at this point, we have almost 0. So we have a posterior of 0. If we consider, for example, this point where the two class conditions are the same, then the posterior is the same, half and half. It's okay? So for each value of x, we can compute this posterior, which means, well, it's quite probable that if I have a measure in this range comes from class 1, while if I have a measure in this range, more likely this measure comes from class 2. It's okay? Someone okay, the other thing is recording. Okay, someone has started recording. Okay? It's okay? Is that more or less clear?
Yes.
Okay. The problem is that we almost never know these distributions. I mean, we suppose this distribution exists, but we don't have them. We only have data. In very easy problems, we can estimate this distribution from the data. If this is the case, then we could construct this posterior probability, and then once we have this posterior probability for all points in my space, then the way to assign a class to a point, that is, now we want to construct a classifier. You give me a measure, and I answer class 1 or class 2. How can we construct this predictor? Well, just compute posterior for x, and then select the maximum of the posteriors. It's quite logical, isn't it? This is what is called the Bayes rule, which is exactly this. The mapping from the input space or representation space to the classification space for any point x is equal to class 1 if the posterior for class 1 is greater than the posterior for class 2, is class 2 if the posterior for the class 2 is greater than the posterior for class 1, and it's undefined otherwise. Well, this undefined is because in some places of the space the probability can be undefined, and also because we can have a tie between the two classes. So if for example, here at this point, the classifier gives us a undefined, because the probability of this measure coming from class 1 or class 2 is the same. It's okay? In practice, in this case, you can output whatever you want, class 1 or class 2, just random, for example. It's okay? Questions? No? No questions? I see some bells, but I don't know if someone, okay. Well, so this is both these distributions and the Bayes rule that can always be obtained from these distributions is something that is always present, but in the theoretical point of view. I mean, we assume that all of our problems have these distributions, but the problem is that we don't know them. And sometimes it's very, very hard to estimate these distributions. But nevertheless, we may assume that they exist. So the Bayes classification rule is the optimal possible rule if all our assumptions about this distribution hold. For this rule, we can compute which is the true probability of error. The true probability of error for each point x in the space is given by precisely the posterior of class 2. If the posterior of 1 is greater, this means that our predictor, the optimal predictor, has set class 1, but the probability, posterior probability of class 2 is not 0. So this probability is the probability of error in this at this point. Graphically, if this is the posterior for class 1, this is the region of the space where the classifier answers class 1, and this is the region where the classifier answers class 2. For example, at this point, the classifier says class 2, but the probability of coming from class 1 is not 0. This is exactly, this value here is exactly the probability of error at x. And the same for every x in my space. If we average this over all the space, we obtain the global probability of error. So if we were able to compute this, and we can do this for easy cases, then we have an estimate about what would be the best possible probability of error. It's okay? Which is nothing but this. I mean, we can, because this integral becomes the area under the curves. It's okay? Questions?
No.
So in other words, the probability of error is proportional to this area here, or this area here. This is for errors from class 1, and also this area and this area. And the sum of the two would be the global probability of error. I mean, proportional to these areas. If these areas become 0, then the probability of error of the Bayes classifier is 0. It's okay? Sometimes we can classify also with a rigid option. This means we have two classes. We can classify into one class, the other class, or we can say that we are not sure about the classification. This happens here when we have, for example, equality between probabilities. So as an extension for that, we could think of a reject option in which we can not decide if the posterior probability is not above a certain threshold. We're not going into details, but let me just show it graphically. So we can select thresholds. They can be separate for class 1 and class 2, or they could be the same, doesn't matter. The thing is that once I compute the posterior for class 1, instead of selecting just the maximum of the two posteriors for each x, I also check that this posterior is above the threshold corresponding to class 1, which is this one. So for these values, I answer class 1. For the same reason, the second threshold for this area, I answer class 2. And in this area, I say nothing, reject. It's okay? So in that case, my predictor is class 1, class 2, or reject. I'm not sure. It's okay? This can be very convenient in some particular and practical problems, and this is just a slight modification of the previous classifier. It's okay? Any questions? Okay, my intention now is to do a little exercise just to make sure that you really understand these kind of things. So if you don't mind, I need to just set up the exercise, and then you can spend the next 10-15 minutes doing this exercise. So let me, the exercise would be exercise 2.1 in the virtual system. No, not here. Here. Let me check. Okay, so today is 10. And what time is it? Let's say okay, check if you have this exercise in your, oops, sorry.
No,
What now?
I don't have it.
Have a look again in the virtual system.
I have it.
Exercise 2.1.
Yes, now, yeah, now it is.
Okay, this is an exercise you have to be done in a piece of paper. So something like this. It's okay? Let me just introduce the exercise and then you work on your own. So we have an space of 1 dimension. And we are told that we have 3 classes and that our classes have prior probabilities of 1/6, 1/3, 1/2. The sum of these has to be 1. It's okay? And on the other hand, our distributions, the class conditional probabilities of each class for class 1 and class 2 are uniform between 0 and 1 and between 1 and 4. Please check the statement because I did it very quickly. 0, 1, 1, 4. And then the third class distributes linearly between 1 and 4. So in other words, a uniform distribution is something like this. It's okay? Between A and B, distribution, uniform. It's okay? 0, otherwise. While in the linear case, also between A and B, we have something like this. It's okay? Linear, uniform. Oops. Uniform. It's okay? So, well, what is the value, the value of this and the value of this? Well, take into account that, oops. Take into account that this area has to be 1 and that this area has to be 1. So this value needs to be B minus 1. Sorry. 1 divided B minus A, isn't it?
Yes.
Yes.
Okay. And this value here needs to be 1 over B minus A divided by 2. Sorry. Two. Do you agree?
Yes.
Because the area has to be 1. It's okay? So if you want, we can start plotting some of the probabilities. For example, the class conditional probability of class 1 in this example is uniform between 0 and 1. This means that is something like this. It's okay?
Yes.
Because the area is 1 by 1 is 1. So in the second case, between 0 and 4. So this means that do you agree? This area is 1. This area is also 1. And the third one goes from, let me check it. It should be 3 2/3. So it should be something like this. Exactly. Because this area is also 1. So is that clear?
No, can you repeat?
From where exactly?
The green part, the green area.
Well, this is a triangle. The base is 3.
Okay.
The height should be 2/3 because 2/3 multiplied by 3 is 2 divided by 2 because it's a triangle is 1. So this green area like this is 1. In general, for any A, B points, the uniform distribution of this linear distribution, this value has to be equal to what you have here. Oops. It's okay? In our particular case, we have that. It's just a very, very easy and toy problem, just to force you to work with some numbers. You don't need the form of this function, but if you want, the function is exactly this one. But you don't need that to do the exercise because you should do the exercise graphically. It's okay?
Yes.
Okay, so please go ahead, take a piece of paper and please do the exercise. You can talk if you want. I mean, you don't have to, but I want you to upload the result. It's okay? Questions? How is it going?
I did it already.
I see
I
there is
think.
one submission. 2 submissions. The task is still open for a few minutes. No, but the task is open, or should be. Okay, let me check. Oops, no. Sorry. Now it's open. Please upload. Still 5 more minutes, but I mean, the sooner you upload. I need you to upload something, even to say that you don't understand it or whatever. So please upload something. 2 minutes. Okay. Well, does any of you, okay, the task is now closed, well, or at least almost still open. Okay, the task is now closed. Does any of you wants to share his solution or comment on his solution? Someone? No? Okay, I had a quick look on some of the submissions, and the things I was looking at were not. Okay, let's comment on the exercise. Well, I assume you have understood the statement of the problem. I mean, here you have the starting point. I mean, we have three classes, we have one dimension, we know for sure how measures are distributed because someone gives us priors and someone gives us class conditional probabilities. It's okay? From this, we have drawn this graph on the left. And now the exercise says draw the following. The class conditional probabilities, well, is what we already have. The unconditional probability Px. We are not supposed to compute this, just to draw it. The sum of the three would be this. From 0, it would be exactly the same as the blue line. Let's plot in a different way. Would be something like this. Oops. From this point, we have the sum of the red line and the green line, which is exactly this. And the same. Do you agree?
Yes.
Yes.
Do you all have drawn this? Or do you all understand that this is exactly Px?
Could you please explain again?
Yes. The blue line, which is the uniform line between 0 and 1, is the class conditional probability of class 1. The red, class 2, and the green, class 3. Px, the unconditional probability, is the sum of the three. So the sum of the three between 0 and 1 is exactly Px W1. And between 1 and 4, we have a constant function. The red one is a constant, and the green one is a linear function. And the sum of the two is exactly this. It's okay?
Yes.
What else? Now we are supposed to draw the posterior probabilities. Posterior probabilities are equal to the class conditional probability, this is capital P, a class conditional probability of the same class weighted by the prior and divided by the unconditional. This is the formula you have in the slides. It's okay?
Yes.
So the first step is to compute this. So now you have to weight the functions, the class conditional probabilities you have here. Let's do it easily. Okay, and now okay, to weight this, we have to multiply each of these class conditional probabilities between by the prior. For example, this blue line has to be multiplied by 1/6. It's okay? Okay, instead of moving this, because we are going to have very narrow figure, let me instead change the scale. And let's try and now it's okay. This is the class conditional probability of class 1 weighted. Okay? Now the area, this area is no longer 1, now is 1/6, which is the prior. Okay?
Okay.
Let's consider class 2. Class 2 has to be divided by 3. So it was, so it is more or less This is supposed to be, please check if I'm wrong or not, because I'm not absolutely sure. This is 1/9. It's okay? Because it was 1/3 divided by 3. It's okay? And what about the green line? The green line has to be divided by 2. So it was 2/3, so 1/3, so it's like this. Okay? Questions? This value here was 2/3. Now is 1/3 because I changed the scale. So now again, are you sure that this is the correct unconditional probability? Are you sure that this unconditional probability is the correct one? This is the definition of the class unconditional probability. So this is not the correct one. Do you agree? I cannot see you. I don't know if you are agreeing or not. Someone is writing something, but I don't. What needs to be divided by px? Hello? Is somebody there?
Yes. I don't know, at least.
Well, I just showed the formula for the unconditional probability.
¿Puede ser que lo que esté mal sea el eje Y?
¿El eje Y? ¿Por qué?
Quiero decir que en vez de ser de 0 a 1 en 1, pues sea un sexto.
Well, yeah, but the thing is that what we have plotted here is just the sum of the conditionals, while the correct definition is the sum of the weighted conditionals. So it's not the sum of the above, it's the sum of the new ones. So we have to do the same we have done here, but here. So the unconditional probability, in fact, is this value. Well, more or less. I mean, take into account that Px is a distribution. The integral has to be 1. And if you have a look, if this blue area is 1, so the area under this black curve cannot be 1. So this is not correct. This one is correct. So going back to the exercise, this is the answer of the first item. This is the answer of the second item. And we still have to compute the posteriors. Okay? These are the weighted conditional probabilities. This area here of these colors are exactly equal to the priors. And the sum of the three is this black line, and the area under the black line has to be 1. And it is 1 because I have changed the scale. It's okay?
Yes.
Okay, now we need to compute the posteriors. To compute the posteriors, we have to divide the weighted class conditionals by the unconditional. You could plot everything in the same graph, but I mean, it's going to be a mess. Okay. The class conditional of the class 1 class 1 okay, it's easy to now let's change again the scale. 1 and 0. Because class 1, we have this blue line divided by the black line, which is the same in this range. So we have exactly this. 1 between 0 and 1, 0 otherwise. This is the posterior it's okay. What would be the posterior of class 2? Well, the posterior of class 2 would be At this point, exactly at this point, the value of the red line is 1/9. And the value of the black line is also 1/9. So the value will start here. It's okay? And then at this point, the value of the red line is still 1/9. And the black line, if I'm not wrong, would be, I don't know, something like this value here. But also take into account that the green line is something like like what? I mean, let me. What I want you to understand is that the value of these posteriors at this point is 0.5 for class 2, 0.5 for class T, for class 3. It's okay? This value is decreasing from this point to this point and keeps decreasing until this point. No, not exactly to 0. Sorry, not 0. Let's check what happens at this point. I don't know if you are agreeing or not. If you say nothing, well, I use the formula. I've seen you were putting formulas, but I don't know you to write formulas. Writing formulas is just copying what you have in the slides. I want you to understand what's happening. And I think it's better to plot it graphically, at least for an easy example like this. I don't understand your questions. Okay, what's the value of the posterior? Here. Okay, so this is 1/9. This is 1/3. And this is which is 2/9. And this is the sum, which is 3/9. So the proportion of the posterior for class 2 and class 3 is 1/3, 2/3. So it has to be 1/3, 2/3. So it means that this has to be something like this. And you understand this? And the third one is a linear function divided by another linear function. This is a constant function. And this constant function has to be let me sorry. Well, the exact shape, oops, sorry. The exact shape should be something like this. Because the sum of these two has to be 1. Well, we are not plotting exactly. That's not my intention. My intention is to just show what happens. So in other words, from 0 to 1, the posterior probability of class 1 is 1 and 0 the others. Then from 1 to 2, the posterior of class 2, the red one, it starts at 1 and the third starts at 0. Then progressively, this value decrease and increase. Oops, I plotted. Okay, let me plot this better.
I have a question.
Yes.
The joining point, that is the question.
Yeah.
Should it be at 2? I was going to ask.
Yeah.
Okay.
Has to be. At this point, which is this point, the two posteriors are equal and they have to sum 1. So it's 0.5, 0.5. It's okay? And from this point on, then the posterior of the green is superior to the red one, but never arrives at 1 because never the red ones go to 0. It's okay?
Yes.
So this would be more or less, if you want to lose a bit of time, you could try to plot this exactly, or even you can compute the functions. I mean, it's a nice exercise, but perhaps too long. I just want you to plot the things and understand. So this would be more or less the plots of the 3 posteriors, which are the ones that gives us the possibility of defining, at least graphically, the Bayes classifier. The Bayes classifier would be something like this. Decide class 1 between 0 and 1. Decide class 2 between 1 and 2, and decide class 3 between 2 and 4. What happens exactly at 1? Undefined. What happens exactly at 2? Also undefined. What happens at 4? What happens at 4?
Would it be class 3?
Class 3, yes. The same as at 0, class 1. But what happens above 4? Undefined. And below 0? Undefined. It's okay?
Yes.
These areas or regions or points in this case where the classifier is undefined because 2 or more of the posteriors are the same, because the problem is that here all of them are 0. Here 2 of them are the same. Here 2 of them are the same. So these areas are called decision boundaries. It's okay? What would be the probability of error? Let's go to the definition. The probability of error is the integral of the probability of error for all x. But this probability of error, it's the posterior. Exactly the posterior. But the posterior, remember that the posterior is the weighted conditional divided by px. It's okay? And oops, I think there is an error. Sorry, I think that well, this is not exactly this. This is this. So when we compute this probability of error, we have to weight this probability of error by the unconditional. That's the definition. I mean, we cannot, I mean, if this is the one class, this is another class, and this is the unconditional, I mean, errors here cannot weigh the same as errors here, because we have here more probability of having points than here. So that's why this factor appears here. And this is this, and this is this. So this P here and this P here cancel. And to obtain the error, this error is also equal to the integral of the weighted conditionals. You see? Anyway, graphically, if we want to display here the probability of error, we have to obtain the areas of the weighted class conditionals in the places where the classifier fails. So, for example, probability of error just for class 1. What's the probability of error in class 1? The classifiers decides class 1 between 0 and 1. Is there a possibility of having errors in class 1?
No.
No, because the decision we take is just there. So there are no blue points over that line. So this is 0. Probability of error in class 2. Well, as we said, we decide class 2 between 1 and 2. Are there red points at the left of this point? No. But are there red points at the right of the value of 2? Yes. Can you see? Can you see that?
Yes.
If we computed the integral of the posterior of class 2, sorry, posterior of class 2. Just like this, then we would obtain this area. But this has to be weighted by Px. And this is exactly the same as which is that. Do you understand that? This area is very easy to compute because it's that. It's okay? Questions? Is that clear or not? Well, what about the third one? Well, the third one is the same reasoning, and now the area here would be this, but this area is not exactly the error because we have to weight this area by the unconditional, which corresponds exactly to this area here. And this area is also very easy to compute because it's this. It's okay?
Yes.
Okay. So the sum, well, I'm not sure if this is correct because I haven't done this before, so I assume it's correct. If not, you just check it and tell me. So the probability of error, it's 5. For this very easy problem. It's okay?
Yes.
And the decision boundaries
Okay.
Oops. Questions?
No.
Okay. The goal of this, we never need to do things like that because even in the case we suspect that we know or we can estimate these distributions, what we do is we compute that in the computer, and we never done things like this. But I just want you to deep into that and to understand the concepts. Okay? Class conditionals, priors, posteriors, Bayes rule, and probability of error. It's okay? If there are no questions, we can go ahead.
No question.
No questions. Okay. Okay, so this Bayes classifier, it's, as I said to you, is a theoretical thing, but for very easy problems in which we can estimate or know by any means the distributions, then we can program and use this Bayes classifier. We are going to see some examples. For these classifiers, for these particular ones, and in other more general cases, we will define a way to represent a large number of different classifiers. This common formalism is what we call discriminant functions, which is the following. Instead of having a mapping from X to W11 or whatever, instead of that, we will define another mapping from X, and then we will have an output for each class. Let's say class 1, class 2, up to class C. C. It's okay? These outputs will be, each one of these would be a real value. So each one of these outputs corresponds to a usually continuous function. And once we have these outputs here, then we compute a max. Well, in fact, an arg max. This one. Okay? And whatever class gives the maximum value, then this is the output we give here. It's okay? So it's quite common to decompose this class mapping into this set of mappings, one for each class, and then to compute a maximum operation. Okay, each of these functions are called discriminant functions. It's okay? And now we know a first example, because in the Bayes classifier, it happens that the posterior corresponds to the discriminant function of the Bayes classifier. It's okay? Okay, so we are going to extend this scheme not only for the Bayes classifier, but for a large number of different classifiers. The other interesting thing is that the discriminant function is not unique. In fact, we could remember that this posterior is the posterior, it's the prior, the class conditional divided by px. This prior depends on I, this conditional depends on I, but this is unconditional. You see? So if instead of the posterior I take this is also a discriminant function of the same classifier, because this term here does not depend on the class. So when I take the max, the result would be the same. You see?
Can you repeat it, please?
Yes. We've seen that the Bayes classifier is the one that gives the maximum of the posterior. This means that the posterior is a discriminant function of this classifier. What if I multiply this posterior by px, which is independent on the class? If I multiply this by px, then the factor px, which is here, disappears.
Okay.
So I can take the weighted conditional also as a discriminant function of the same classifier.
Okay.
It's okay?
Yes.
In fact, I could apply any monotonous function. For example, I could take the log of the prior by the unconditional. The log of all this. I could take this instead of this, and the classifier is the same, because the maximum of the logarithms is the same as the maximum as the weighted conditionals. It's okay? I mean, I can modify this discriminant function as long as the maximums doesn't change. So I can divide by a value, I can divide by whatever. I can apply a monotonous function as, for example, the logarithm, etc., etc. It's okay? Okay, some definitions we call acceptance regions at the regions that correspond to each class. Acceptance regions, graphically, here, for example, this would be the acceptance region for class 1, and this would be the acceptance region for class 2. In this case, we have a reject region. The decision boundaries correspond to the places where two of the discriminant functions are equal. It's okay? And usually, when we only have two classes, instead of using two discriminant functions, it's quite common to define a unique discriminant function. In this case, instead of taking the max of two functions, we use the sign function. So when this function is positive, then class 1 is greater. When this function is negative, then this class is greater. It's okay?
Yes.
Okay, this is the usual thing. Questions? What time is it? Let me check if we can have a look at some of the examples, because I don't want to. Let me. Okay, let's take one of the examples we had in I can't remember whether we had a look at the code in the examples. Just okay. Can you see?
Yes.
Okay, we were having a look. We will go deeper into these examples, but I mean, I can't remember exactly what have we seen here. But I mean, we okay. Just to have a quick look. Yeah, I think this will serve us. Okay. This is the toolbox we are going to use. We are not going into details, but I mean, we load data. We have the representation of this data, the labels of this data, and we obtain a mapping here. We will talk about this particular mapping later on, but now it's just a mapping. It's okay. Well, when we fit this mapping, then my mapping is able to predict things. Mapping is WC. Let me run this. Okay, the thing I want to check is that this is the mapping. When we say WC, for example, and the data is X, this is the whole data set. But for example, this is just one example. Can you understand this without going into details? The data here has 4 dimensions, and the value of each dimension is 5.1, 3.6, 5, sorry, 1.4, 0.2. This is the X, the values corresponding to one of the examples. The label of this is 0. This is the true label. It's okay? The mapping can predict by giving as input whatever you like. For example, this. That's because well, this is a Python thing, okay? So this is what this is the input. It's the same as you can see. It's okay? So giving this input to predict, to the method predict, I obtain 0. So 0 is the prediction by this mapping. But also associated to this mapping, I have decision function that is exactly with what we have just seen in the slides. If I give to this the same input, then I obtain 3 values. These 3 values are the 3 discriminant functions for this input. What's the maximum of these 3 values? What's the maximum? The first, the second, the third? Are you there? The first. The third, the first, of course, the first. That's why, because 0 is the first. For example, if instead of just 1, we give the, I don't know, the first 5. So these are the 5 predictions. In all cases, the maximum is the first. And in all cases, the prediction is 0. It's okay? This is quite usual in a large number of particular classifiers. Sometimes these discriminant functions correspond to probabilities. For example, here, in this case, sorry. In this case, we also have this predict proba and also predict log proba, which means that for any input, we can obtain either the prediction or the decision function or the probabilities. So in this case, the probability of class 0 is almost 1, as you can see. And also, these are the logarithms of the probability. All of them are valid discriminant functions of the same classifier. It's okay?
Yes.
Not all the classifiers have this possibility, but most of them have. Questions?
No.
Okay. In the next class, we are going to see these concepts of probabilities and decision functions in a particular case that involves Gaussian distributions. Because Gaussian distributions are, well, when we have like noise or we have measures that correspond to simple processes in which we have a typical value and that dispersion, we have a lot of measures that can be modeled as Gaussians. So the Gaussian case, traditionally, not in practice for complex problems, but I mean, traditionally, there are problems that can be solved using modeling the classes as Gaussian. In the case of Gaussians, we can also write and obtain specific classifiers that are not as easy as the one we've seen in the example, but they are not so difficult. So we will have a look at how the classifiers, the boundaries, and everything looks like when we have Gaussians in any number of dimensions, of course. It's okay. You can go ahead if you want in the slides and have a look at what we have. It's okay?
Yes. Okay.
Okay, if you don't have further questions, we will leave. I want to ask you a question. Can you access all the recordings of the classes? By the way, we can stop already this. Do you have access to the recordings or not?
Yes, I have downloaded the 2 last classes already.
Okay, because I had an email or a message from somebody telling me that wasn't able to download the recordings. So you can access them without problems.
Yes.
The last one gave me some problems to download, but the first one didn't.
So I don't know, just